Hi there. In this video we're going to examine aim constraints step by step to understand how they work. And whatever your 3D package calls these, the functionality is still identical. This is in fact one of the main advantages to using aim constraints in advanced character rigs. Because they use vector math rather than Euler angles to compute orientation, they work predictably across all platforms, independent of rotation order, and they can be very easily recreated procedurally in a game engine, making them compatible with keyed animation as well as with procedural animation techniques like ragdolls, human IK, endorphin, and so on. Let's start off by creating an aim constraint using the default settings. As you can see, the x-axis of our constrained object in the center is now aiming at our target object on the left. If we move our target object, the constrained object will continue to seek it. This behavior is pretty self-explanatory, but unfortunately also very limited. If we want to do something more complicated than a spotlight pointing at a target, we may see our constrained object flip at times. For instance, if we move our target object across the YZ plane, you will see the Z-axis of our constrained object flip back and forth. The reason for this is because there are some more complex properties associated with the aim constraint that we need to manipulate in order to control its behavior. So let's open the attribute editor and take a look at these properties. The options that you see here are the same that exist if you were to open the expanded view for the tool when you create the constraint initially. What you see here are various three-part input fields. Offset allows you to specify an initial angular offset for the object using Euler angles, whereas the fields for aim vector, up vector, and world up vector correspond to x, y, and z components of vector values. The aim vector field is of particular interest because this specifies which axis of the constrained object should aim at the target. Because this axis currently has a value of 1 in the x input field with 0 in the y and z fields, we are pointing with our x-axis. If we were to change this to a value of 0, 0, 1, you can see that we are now constraining our z-axis. So let's return to our problem of flipping that we saw earlier. In order for an aim constraint to know what to do, it needs an additional up vector constraint to sort of provide a hint for the object so that it knows what to do with its remaining two axes. We provide this information using the remaining inputs. The first of these is the up vector input field, which tells us what axis on our constrained object has the up vector constraint. Our current value of 0, 1, 0 means that our object's y-axis has the up vector constraint applied. The next important input is the world up type drop-down menu. This specifies what in our scene is constraining our object's up vector. These values can be none, which means that we have no special axis constraining our object's up vector, scene up, which corresponds to our world's y-axis, object up, which corresponds to another object's y-axis, object rotation up, which allows us to use a custom axis from another object, or finally vector, which allows us to use a custom world space vector. With our current setting, we can specify a world space vector to constrain our object's up vector. By changing this to a value of 0, 0, 1, we can use our positive z-axis in world space. This means that our y-axis, which we specified as our up vector, will try to match our scene's z-axis. Now that we have specified all of these settings, you can see that our constrained object no longer flips when it rotates through the range of motion that was causing problems earlier. What happens, however, when we are not simply moving the target in the xy plane? You can see that our up vector, the y-axis, no longer constrains itself exactly to the z-axis. This is because the aim constraint's primary job is to make sure that our aim vector, the z-axis in this case, is always looking at the target. The up vector's constraint therefore appears to be a hint or approximation. What then is the logic that controls this? It is important to understand what is actually happening so that we do not just tinker around blindly. We want to create a specific function that produces the result we need. Let's create an example by exploring the aim constraint options a little more. First, let's change the world up type from vector to object rotation up. Remember that this allows us to use a specific axis from another object in the scene. In this case, I want to use this third object, which I named UpObject1, so I will type its name into the worldUpObject field. I want to use its y-axis as my constraint, so I will go back and change my worldUp vector value back to 0, 1, 0. To summarize, we're currently telling our constrained object in the middle to point its z-axis at the target on the left, while using the y-axis of our helper object on the right to constrain its own y-axis. As you can clearly see though, our constrained y-axis is not, however, identical to the y-axis of our helper object that it's trying to copy. In order to understand how we are actually producing this final result then, let's go through the process the computer is using, step by step. The first step is of course that we are telling our constrained object to point its z-axis toward the target on the left. The problem, however, is that we need more information. This is because there is actually an infinite number of valid configurations for the other two axes that would still satisfy our constraint. What we need therefore is to give the computer information for at least one other axis, our up vector. In this case, we're getting our up vector constraint from our helper object. We therefore now have a z-axis which is pointing at our target, and a y-axis which is copying our up object's y-axis. The next step is to figure out where our third axis is. Fortunately, using vector math we can compute the cross product of our two existing axes to solve for this third axis. The cross product basically finds a plane in space made by our two known axes and then computes a third vector that is perpendicular to this plane. Since there are actually two opposite vectors that may be possible solutions in this case, the computer uses what is called either the left-hand rule or the right-hand rule to figure out which one to use. As you can see, our computed x-axis forms a 90-degree angle with our z-axis as well as with our y-axis. The final problem, then, is that our object's axes are not orthogonal, meaning that they are not all 90 degrees with respect to one another. This is because the z-axis and the y-axis that we are supplying to the constraint were not at a 90-degree angle with one another to begin with. What we do then is compute another cross product. Because constraining our z-axis is our primary concern, we need it to remain fixed. However, now that we know our x-axis forms a 90-degree angle with our z-axis, we know that their cross product would form a perfectly orthogonal set of axes. We therefore recompute our y-axis as the cross product of the other two, and we have our final constrained set of axes. You can now see why the up vector appeared to be an approximation of the axis it was supposed to copy. In fact, a very specific and predictable set of rules determined the final result. Hopefully, now that we have stepped through this process, you have a better understanding of how aim constraints actually work. Instead of just fiddling around and hoping that you stumble across the right solution, you can now think about how your constrained objects need to behave throughout their ranges of motion. You can use this knowledge to solve a lot of complex rigging problems simply by manipulating constrained up vectors. Thanks for following along.